Welcome to the deep dive. Today, we're tackling something really fascinating. How complexity, um, amazing order really, just sort of emerges from chaos. We see it in living things, of course, but also in non-living matter. Normally if you want to build something, you grab a blueprint, you force things together like uh, Lego bricks, snapping them into place.
Right, very deliberate.
Exactly. But the molecular world, especially inside a cell, it's not like that at all. You have these incredibly precise biological machines forming out of parts that are constantly, well, jiggling around, all this fluctuating noisiness, as scientists say.
Constant motion.
So the big question for you listening is, how does life get so reliable, build these large, stable structures from what's essentially a jittery herd of molecules, without placing every single atom? And maybe even more exciting, could we use that trick ourselves in engineering?
Yeah, it's a fantastic question and a huge challenge because living systems are what we call far from equilibrium. They're constantly processing energy.
Not just sitting there statically.
Exactly. And honestly, our theoretical grip on that kind of system, it's historically been a bit thin on the ground.
Huh.
So today's deep dive is all about exploring new ideas in non-equilibrium statistical mechanics. We'll trace how thinking has evolved and introduce this really powerful concept, dissipative adaptation.
Okay.
Our mission, really, is to see if we can uncover some general physical principles behind how things organize themselves, especially inside cells, and think about how we might actually apply that, for nanoscale design.
Right, let's start with the basics then. Maybe clarify the difference between systems at equilibrium and those pushed away from it.
Good idea. So equilibrium is like, imagine a sealed box of gas you just leave alone forever. It settles down.
Yeah.
The chances of finding molecules arranged in a certain way, it follows a pretty simple rule, an exponential one, the Boltzmann distribution. It's predictable.
Predictable, okay. So non-equilibrium is less predictable.
Much harder, yeah. Because when you have external forces constantly doing work on the system, pushing it, driving it, the probability of a state isn't just about its energy right now. It depends on the whole history, the sequence of configurations it went through.
The path it took.
The path, exactly. And that forces you to think about things like time reversal symmetry. Why do things tend to go forwards and dissipate energy, not just spontaneously run backwards?
Ah, okay.
And the first really big step forward, theoretically, came from Lars Onsager. He realized how important this time reversal idea was, even for relatively simple driven systems. He showed their dynamics followed these reciprocal relations.
Reciprocal relations, like a give and take.
Sort of, yeah, a hidden symmetry. For instance, he found this fixed relationship between electrical current driven by a chemical difference and the chemical reaction rate driven by a voltage. It showed this subtle underlying connection.
And that led to Ilya Prigoghine's work, which really caught people's attention, right? He looked at non-equilibrium steady states.
That's right. Not systems changing wildly, but systems with a constant flow running through them. Like a river, maybe, constantly flowing, but looking roughly the same over time, sustained by the water source upstream.
Instead of a stagnant pond, which would be equilibrium.
Exactly. And using Onsager's ideas, Prigogine realized something quite profound. The steady state these systems naturally reach is one where the total rate of entropy production is actually minimized.
Minimize entropy production, okay.
Yeah, so he proposed that maybe many properties of life, these dissipative structures, he called them, could be explained by this tendency, a kind of fundamental organizing principle driven by minimizing waste, in a way.
That sounds powerful, a principle to predict long-term behavior just by optimizing something.
It was exciting. It offered a potential handle on complex systems. But, well, the real world, especially the biological world, turned out to be more complicated.
It often does.
Prigogine's formula, this minimum entropy production principle, it often breaks down, especially in what's called the nonlinear response regime. And that's precisely where many living systems operate.
Okay, nonlinear response regime. Can you break that down quickly?
Sure. Think linear's like pushing a swing, gently push harder, it goes proportionally higher. Predictable. Nonlinear is more like pushing a switch. A tiny push might do nothing, then suddenly click. A huge change. Or maybe pushing harder makes less happen because of complex interactions.
Got it. Like feedback loops and things.
Exactly. Biological systems are full of those. So the simple optimization rule didn't always apply. We needed a shift in perspective.
From looking at states to looking at...
the paths, the dynamical trajectories. How does the system actually get from A to B over time? Not just comparing snapshots, but comparing the whole movie, you could say.
Right. And that shift leads us to Gavin Crooks and Chris Rosinski. This sounds like a key moment.
A huge moment, absolutely central. So Gavin Crooks, in 1999, developed the fluctuation theorem. It's this really exact mathematical expression about the likelihoods of different paths a system bouncing around due to heat might take.
Likelihoods of paths.
Yeah. The core idea is that any specific path, any microtrajectory, is more likely than the exact reverse of that path by a specific amount. And that amount is related exponentially to the heat released into the environment during the forward path.
So releasing heat makes a path more likely than its reverse.
Essentially, yes. It quantifies the arrow of time at the micro level based
Yep.
on energy dissipation. And what's amazing is this holds even if you're driving the system with complicated, changing external forces.
And Jasinski's equality, he mentioned that's maybe the most famous result.
It is, came a bit earlier in '97. It's a really elegant consequence, linking the work you do on a system when it's not in equilibrium to the change in a core equilibrium property called free energy. It built a bridge between these two worlds.
Okay, that sounds useful. But you also mentioned an extension of the second law came out of Crookes's work.
Yes, and this gives us really helpful intuition, I think, for understanding these far from equilibrium systems. Let me try to simplify it.
Please.
Think about a process that's really, really irreversible, like scrambling an egg. It just doesn't unscramble itself, right?
Right.
This extended second law basically says, the more statistically irreversible a spontaneous process is, the less likely its reverse path is, the greater the minimum amount of total entropy increase required.
More irreversibility means more entropy.
More entropy produced, yes, which generally means more heat dissipated. So greater irreversibility has to be powered by more of the work done on the system being dissipated as heat rather than being stored up in the system somehow. To really lock in that one-way street, you have to pay an energy toll in the form of dissipated heat.
Okay, I think I'm following. Are there examples?
Definitely. Think about computing.
Yeah.
Ralph Landauer showed decades ago that erasing information, which is an irreversible process, has a minimum energy cost, minimum heat that must be dissipated. You can't erase for free.
Huh. Never thought of it that way.
Or in biochemistry, think about ATP hydrolysis. Cells, couple reactions they want to push in one direction to the breakdown of ATP. That release of energy makes the overall process highly irreversible. It pays the dissipation cost to ensure things go the right way.
So this framework lets us think about these costs more generally.
Exactly. And the great thing is, we don't necessarily need to know all the microscopic details or assume things are in local equilibrium, which was often a fudge factor before. We can look at the overall process, the inputs, the outputs, the dissipation. It's much more powerful for messy, complex things like living cells or trying to build things at the nanoscale.
And connecting this back to self-assembly, how does this help us understand that?
It gives us a direct link. The amount of extra energy you spend is dissipated work while building something. That sets an upper limit on how durable that structure can be.
Ah, so dissipation buys you stability.
In a sense, yes. If you know how fast something was assembled and how much energy was dissipated, you can immediately get an estimate for its lifetime, how long it's likely to stick around before falling apart due to thermal noise.
And the flip side, if you want to build faster.
If you want to build faster and maintain the same quality, the same durability, well, the principle suggests it should cost you more dissipated work. It's a fundamental trade-off between speed, stability, and energy cost.
Okay, this is really setting the stage. So let's unpack the core hypothesis you mentioned earlier, dissipative adaptation.
Right. This idea flows directly from Crookes' theorem, from that link between path probability and dissipation. Imagine a system being driven maybe by light or chemical fuel or mechanical forces. It can explore many different shapes or configurations.
All that jiggling we talked about.
Exactly. Now, if lots of different configurations are sort of equally easy to reach kinetically, meaning no huge immediate barriers, the ones that end up being the most likely outcomes of this driven process are those that have histories where they consistently absorbed and dissipated energy effectively.
Why them specifically?
Well, the intuition is surprisingly simple, actually. Absorbing energy from the drive lets the system jump over energy barriers it couldn't cross just with thermal wiggles.
Okay, it gets a boost.
It gets a boost.
Yeah.
And crucially, if that absorbed energy is then dissipated as heat after the jump, it makes it much harder for the system to just jump back. The dissipation pays the toll for crossing the barrier and makes the change stick. It locks it in.
So absorbing and then dissipating makes the change more irreversible.
Precisely. Irreversibility and heat dissipation are intrinsically linked here. The system uses the drive's energy to make a change and then dissipates some of it to prevent easily reversing that change.
Yeah, okay. Now this is where I think it gets really interesting. You're saying the most durable changes happen when the system is best at dissipating.
That's the idea. While any single change might look random, the changes that persist, the ones that are less easily undone, tend to occur when the system happens to fluctuate into a shape or configuration that's momentarily better at coupling to the drive, better at absorbing its energy, and then dissipating it.
So it's like the system accidentally finds a way to handle the energy flow better, and that shape gets reinforced.
That's a great way to put it. These less erasable changes accumulate over time. The system preferentially drifts towards configurations that resemble those in its past where dissipation was high. It's not aiming for it consciously, of course.
Of course not.
But if you look back at the history, at the final product, it looks remarkably like it has organized itself into a state that's well adapted to absorb and dissipate energy from its specific environment. And that phenomenon is what we call dissipative adaptation.
It sounds almost like evolution, but
Yeah.
purely physical, driven by thermodynamics.
It shares some conceptual similarity with selection, yes. You could think about directed evolution experiments in labs where scientists iteratively select molecules for a certain function. Each experiment might give unique results.
Right.
Dissipative adaptation suggests something similar might happen spontaneously. Even if you get diverse outcomes from driving a system, the hypothesis is that the ensemble of likely outcomes should share certain physical properties, properties related to their shared history of effectively absorbing and dissipating work from that specific drive.
And the potential payoff for us for engineering.
Well, this is the exciting part for you, the listener, perhaps. If this tendency is real and general, it might mean we can use external drives, light fields, chemical gradients, whatever, to subtly guide the collective behavior of many particles. Nudge the herd towards certain useful structures or functions without needing to control every single molecule.
Guiding, not dictating.
Exactly. Harnessing the system's own tendency to find dissipative pathways.
Okay, it's a compelling idea. But theory is one thing. Is there actual experimental evidence? Does this happen?
There are definitely encouraging signs, yes. And interestingly, one of the clearest examples actually comes from a macroscopic system, not nanoscale.
Oh, tell me about that.
Imagine you have a bunch of small conducting beads floating in oil. Now, you apply a strong voltage across the container. What happens?
I have no idea. They just sit there.
Not quite. If you start them randomly scattered, they spontaneously start to move and connect. They form these quite beautiful, dynamic, branched structures, almost like little lightning bolts or trees made of beads.
Wow.
And these structures aren't static, they fluctuate, but they settle into a steady state. And the key finding is that this branched state is characterized by more rapid energy dissipation. The pattern they form actually lowers the overall electrical resistance of the bead collection, allowing current to flow more easily and dissipate energy faster.
So the beads literally arrange themselves to become better conductors, better dissipators under the voltage.
That's exactly what it looks like. They adapt their collective configuration to the drive.
Okay, that's pretty convincing if it happens on that scale.
Then how much more likely might it be on the nanoscale, where you have huge numbers of particles, strong thermal noise, constantly exploring possibilities? The potential seems enormous.
Are there nanoscale examples too?
There are some penetrative but suggestive results. For instance, a study by Ito and colleagues looked at silver nanoparticles assembling under laser light. They found the aggregates formed different shapes depending on the light used.
Okay, that makes sense.
But more specifically, they found the optical properties of the aggregates, how they absorb light, actually shifted. Their main absorption peak moved towards the wavelength of the laser light that was driving the assembly.
So they became better at absorbing the driving light.
It certainly looks that way. They seem to adapt their structure to better interact with the energy source that was building them. It's tentative, as I said, but it points in the direction of dissipative adaptation.
Fascinating. So where do we look next? What are the most promising areas to really test this idea?
I think some of the most intriguing opportunities are in biological or bio-inspired systems, particularly mixtures of proteins, especially those involving molecular machines like AT-passes or GT-passes.
Things that actively use chemical fuel.
Exactly, because these systems inherently couple shape changes and interactions between molecules directly to discrete events of chemical energy dissipation. They are designed to dissipate energy to function.
Can you give an example?
Well, think about the cellular skeleton. There was some beautiful work by Schaller and co-workers looking at actin filaments protein strands moving around on a surface coated with myosin motors, the little proteins that walk along actin using ATP.
Like muscles at the micro level.
Pretty much. And what they saw were these amazing collective patterns, Whole herds of filaments would spontaneously align and flow together in swirling dynamic spirals. These patterns, these dynamical attractors, look highly organized.
And the connection to dissipation.
Well, it's speculative at this stage, but one might guess that maybe this coordinated flow reduces the strain on each individual motor protein. Perhaps it allows them to operate more efficiently, maybe increasing the overall rate of ATP consumption, the overall dissipation.
So the collective pattern itself could be a result of dissipative adaptation, optimizing energy flow.
It's a plausible hypothesis that fits the framework. Whether it holds up requires more detailed study, connecting the observed patterns directly to measured dissipation rates, but it shows the kind of complex dynamic self-organization where this principle might be highly relevant. Time will tell.
It's quite a paradigm shift, isn't it? Thinking about structure arising not just from minimizing energy, like in equilibrium, but from optimizing dissipation when driven.
It really is.
Yeah.
And while the idea itself, as we've broken it down, has a certain simplicity, the implications are potentially vast. And the reality is, of course, incredibly complex.
But the core intuition remains powerful.
I think so. The key takeaway for you listening is just this. Making something irreversible, making a change stick in a fluctuating world, always has an energy cost that must be paid, usually as dissipated heat.
The toll for crossing the bridge.
Exactly. And when these irreversible changes happen by accident in a driven system, it often implies the system must have momentarily found a shape, a configuration that was good at paying that toll, good at dissipating the energy from the drive. It's a kind of non-equilibrium selection pressure.
It certainly offers a different lens for looking at things. It could, as you said, make life simpler for people trying to build nanoscale devices, maybe guide assembly with energy fields instead of complex chemistry.
Potentially, yes. Or just for appreciating the sheer ingenuity of biology.
Yeah.
When you watch the intricate dance of molecules in a cell, maybe part of what you're seeing is this constant, subtle adaptation to energy flow.
So let me leave you with a final thought to chew on. Think about all the self-organizing systems out there. Inside your own cells, yes, but also weather patterns, maybe sand dunes, even how galaxies form structures.
A huge range of scales.
Could some of these incredibly complex, seemingly well-adapted structures owe their existence at least partly to this fundamental drive, this tendency to find configurations that are good at absorbing and dissipating energy from whatever is driving them? Is there a hidden thermodynamic hand guiding the universe's creativity in ways we haven't fully appreciated? What other everyday things might secretly be shaped by dissipative adaptation?